Everybody. Just wanted to give you a brief rundown of the SPI interface. SPI is a synchronous full duplex interface which has a chip enable and a chip select. It's used for high-speed communication between a master and a slave device. The master device initiates transmissions and also has control over the chip select, chip enable, and the serial clock. Because you can transmit in both directions at the same time, there's a master in, which is usually the microcontroller in, and a master out, slave in. However, it is possible to get two microcontrollers to communicate to one another. However, one must be designated as the master and the other the slave. The question of how fast you can run SPI remains open. Every microcontroller has its own upper limit on this one. For the Arduino, we don't expect it to run any faster than about half of the system clock, and often much slower than that. And our system clock for the Uno typically runs about 16 megahertz. Slave selects can be used to choose which device is going to be active, and during the initialization phase, most drivers will allow you to choose which pin is used for your slave select and for your chip enable. Disabling a chip might result in a saving of power. So sometimes people like to disable the chip in order to put it to sleep and allow them to extend battery life. When you read data sheets, you get to see exactly what kind of data is expected by the device. The transfer of control, control mode transfers are based on either rising or falling clocks. And you can choose whether or not you want a rising clock or a falling clock for the transfer of data. That's called the clock phase. And so you can choose the various modes, and you can see they're numbered here in binary as well as in decimal on the left. And this enables you to choose the mode in which you do your transfer. You can typically reassign the pins that are used for the master out and the slave in, as well as the serial clock and the chip enable and the chip select. And as a result of that flexibility, you'll find that different microcontrollers, especially those which are integrated with various devices, behave differently. And so you've got to read data sheets, and sometimes you won't find data sheets, in which case you have to sit there and test which pin goes to which pin on the chip. And you may do that with a continuity tester or with simple inspection and tracing of the board traces, inspection of the board traces. There's an SPI control register, which allows you to not just fill memory in advance of having it transferred, but also allows you to change the status and control of the transfer. There is no error correction. There is no automatic retransmission request, and there is no flow control. What you do is you insert delays in order to do the transfer, and there is no intrinsic acknowledgement. In other words, you can push data out of the master out slave in and expect that the data is being transferred, but unless you're listening for an acknowledgement from the slave, you can never know if you aren't just dumping data out into the ether. So, the status register is set to 1 when the value is shifted out or in of the serial programmer interface, and that is the 7th bit of the status register. And typically what we want to do is set up a driver for a specific device and then use that as a layer on top. What we'll do here now is we'll show a little bit of code, and what I've done here is I printed out serial select, master out slave in, master in, slave out, and the serial clock. And these are all pin numbers that you would find on the silk screen of the Arduino Uno. And you can get those to be printed right in through here, where I simply have some print statements for SS for the chip select, MOSI, MISO for master out, slave in, master in, slave out, and then the serial clock. These can be assigned and reassigned as you like. The example you're seeing in here is for a transceiver called the NRF24L01, and that's a rather complicated looking thing that allows you to take radio and use it for moving data from one point to another. There are a couple of different SPI register bits which can be set and then reset. You can choose whether you want the bits to be set in Big Indian or Little Indian, and this is done with the so-called DORD. There's a master mode which allows you to choose whether you're in master or slave mode when you're doing your transfers. And there's hardware assistance, which is one of the reasons why you have a register for doing this. There's a polarity bit which allows you to set your clock, phase bit which allows you to set the phase of the clock, and then there's a way in which you can divide down the SPI clock speed so that it goes at a rate that is considered reliable for your application. That's sometimes a function of distance as well as power. So to better understand the ideas behind the SPI interface, I present for you this simple block diagram where the master out goes into the slave in, and the master in comes in from the slave out. The serial select always originates from the master, and the serial clock always originates from the master. There's a hardware interrupt request line which you can use as well. However, that's often optional. And then there are these registers: the control register for controlling transfer, status register for the status of the transfer, and then the data register, which gets packed with the data prior to the transfer, and after the transfer you unpack from the register. So typically this is the master-slave relationship. It is little more than a shift register, and in fact the shift register makes a perfectly fine peripheral for a SPI interface. And what you want to do is you want to distribute the serial clock into the shift register so it knows when to shift. And then if you can put something into the shift register, you can use the serial clock to shift the data back out into the master as a response. So it's just a mechanism for shifting data out of a shift register and then into a shift register. And that's it. That's SPI. If you want to do a bus, you can. Here's a slave select which is being used for all of the slaves at the same time. And then you have a serial clock which goes to all of the slaves at the same time. But look how things are chained. Now we have the master out going into the SPI slave, and then that goes into the master in of the next slave. His master out goes into the next slave, and so now we're daisy chaining the slaves with respect to one another. The question of exactly how these slaves will respond to this sort of thing remains open. That is specific to the application. Here's the SPI interface block diagram as it's implemented by the internal CPU. We've got the crystal coming in. That's typically around 16 megahertz. And then we can divide it by at least 2. So that'll give us 8 megahertz or 4, which is, integral powers of 2. And then this is all part of something that you use to set up the clock rate for the SPI clock. And you dare not go faster than, or even at the same speed as, the slowest peripherals, because you want a little margin of safety. And then here's your SPI control register. Here's the SPI status register. And Let's see, what else do we need? There's MISO and MOSI coming out of the pin control logic, the serial clock, and the serial select. And this would go into a chip enable. So that's about it. Let's see what else we need. Here's that shift register we spoke about before. And what else? Internal bus will read and write to the data buffer that's inside the shift register. And there's this clock logic, which is coming out of the SPI clock and is being driven by the SPI clock. And that's going to effectively choose how the serial clock is emitted from pin control logic. And it also controls how SPI control works. What else do we need to know from this? We can get interrupt requests from the SPI controller when data is coming in and is ready. So here's a typical SPI data register being packed with some data. And here's this SPIF waiting for the end of the transmission. That's the is finished flag. And when we're done receiving the data, we just return it. So that does an SPI transfer. So we load the output data into the data transmission register, which is SPDR. That starts the SPI transmission, checks the value of the SPSR. That's the status register, SPSR, ampersand, to detect when the transmission is complete and then returns complete. And so you can use external memory using SPI as an interface, and the memory will allow for synchronous transmission of data into the memory from the CPU. So let's see what this looks like. Here's the typical slave select, data out, data in. That's MISO, MOSI and MISO, and serial clock. And once these are established and defined, then you can proceed to take data. This is the data output pin mode. Here's data input. And in the SPI clock that's coming out, slave select is also an out. So this must be from the master side, since we're making the slave select an output. And then we've got an opportunity to look at some of the examples: barometric pressure sensor display and the digital potentiometer control. We can find those in the Arduino IDE. What you do, here's barometric pressure control, is you go under examples, SPI, barometric pressure control, and there's the digital potentiometer control. And what you do in here is you can see what's been used. They have a data ready pin. They've got the chip select, MOSI and MISO, and the serial clock. And what you can do in here is you can print out those values when the computer first starts the program. So that's kind of nice. And here's how you go about setting things up. Data set ready, data ready pin, is an input. We want to know if the barometric pressure is ready to be read. Chip select pin, that's an output. That's to assert to the barometer that we're ready to start to read from the barometer and to take a measurement. And the rest is just some detail for doing the transfers. Pin assignments can be seen in the ICSP, that's the in-circuit serial programmer, or in the actual pins that are coming off of the Arduino mezzanine bus. And we can find those here. So that's actually a very good way to go. If you've got MISO, MOSI, serial clock, ground, 5 volts, and reset all in one place, then it's a kind of a big win, because this ICSP header is actually fairly ubiquitous with regard to the different Arduino versions, whereas the question of which pin goes to where, that changes as you go from one Arduino to the other. There's no consistency, except maybe within a family, such as the Arduino Uno family. But it's different if you go to something like a micro or a nano or pro mini. And certainly it's different if it's on a DUE. So it looks like data is shifted out of the master's Mega 328. That's what's on the Uno. And MOSI is shifted in. So master out, slave in is out. Master in, slave out is the input relative to the microcontroller. And you just write data to the data register and it goes out, which is just what you want. So to recap, we have the SPI acting like one shift register, shifting into another, and the slave responding on a serial port using the MOSI MISO chain. Serial clock all comes from an SPI clock generator, and the SPI clock generator gets its clock by dividing down the system clock. So what we see from the master mode is the SPI interface has no control of the serial select. Software is doing this, and this is a configuration of an output for one of the bits in port B. If you configure it as an input, you have to hold it high, or else you're going to enter into slave mode. And what we do is we use the SPI in master mode and assert it low and use it in full duplex. The control register for SPI has a series of different bits that we can set. The SPI interrupt flag, an SPI enable, a data order which determines whether we're going least significant or most significant bit first, a master slave select, a clock polarity, and a clock phase change. And what we can do is we can also insert the prescale for our clock. And using the the SPI prescale, we're able to adjust our clock rate. You can see the clock rate bit has been distributed across the SPI status register as well as the control register. This is the SPI control register, SPCR. And the SPI status register also has one of the bits for the prescaler. It's too bad they've distributed it across two registers. That's very inconvenient, especially since they had these extra reserve bits they could have used. But it is what it is. There's an interrupt flag. Once a transfer is complete, you can check it to make sure the transfer is done. And if there's been a write collision, you'll get a write collision flag. The SPI data register is normally packed prior to any sort of transfer. And when the transfer is complete, you should be able to read out of it when it's coming in or write into it on its way out. So here's a little shift register. It's got a serial input, and it's got parallel outputs, and it's got a little clock. You could use the serial clock for that. And so this would be a perfectly fine slave for an SPI interface. And here's a way in which you could configure the SPI interface, giving us data for the so-called Hitachi LCD display. And this is one of those things that has, I would say, just a little bit more detail than you need, but it's interesting to see how they've gone about implementing this. And here is some SPI application code. And here you can see the SPI enable. Here you can see the 2x clock being put on so that you can divide the 16 megahertz by 2 and get a clock speed for your serial clock of 8 megahertz. This is using the DigiPot, which is a multiplying DAC. And what it does is it outputs resistance that changes the amount of voltage that'll pass through. And here's the outline for the small outline package that we use for the 4100 series DACs. And these guys have a serial clock with a serial input, no output at all. They've got a chip select, and then you can have this is a stereo one, so it's got two outputs. And you can have these DACs come in several flavors. This one has multiple channels. So inside of the DAC, you've got a little shift register that's taking in the chip select serial input and the serial clock, and then gives you a serial output. And this is probably too much detail by half for a timing diagram, but it essentially shows you that you have to take the inverted serial chip select and assert it low in order to select the chip. And then the serial clock comes in and then proceeds to strobe in the data as it comes in through the serial input. So if data is latched on the rising edge, and you can change how that works by using the serial control register, you can effectively determine exactly when the input signal is going to be sampled. Here's another SPI peripheral. This is called the 74HC, that's high-speed CMOS 595. And so what this is a an octal bus transceiver of sorts. It's got storage. It's a latch, so it's really an octal bus latch. And it's a transceiver, at least in part, because it's got a tri-state output that would allow you to have the output declared into a high impedance state in case you should need to turn off the system. That way it wouldn't assert the data line at the same time as something else is asserting the data line. And then to get the data back out of the serial peripheral interface, you would use this SPI read. You write off to the data register, and that starts the process. And then you wait for the SPI to finish. Once the clock cycles are done, you get the data. And here's a another shift register. This one's got the serial in. It's got parallel out. It's got a clock in, and it's got a shift or load. And you can go in either direction. It's sort of an interesting way to go. If you have a basic shift register, all you really need is your serial input and a clock, and you can take in the data. This is a 3D rendering of the DAC with the SPI interface, the 4921 from Microchip. And in this 3D rendering, you can see how it's been encapsulated in this metal box, which just kind of makes it cool. Everybody kind of likes a stomp box. Besides, it's hard to kind of step on the plastic box because it gets all broken and everything. So this is our solution to that. And if you want, you can take a look at the Kickstarter project for this, and you can see it came out kind of nice. So that's the metal box versus the plastic box. And it's got the same electronics in it. I mean, there's really no difference except for, well, except it's metal. Kind of makes it nice. That takes a surprising amount of machining, especially because we've got these square holes. Machining square holes is unbelievably difficult. We start off by drilling a hole, then we get a file out and we square off the hole by hand. It makes it impossible to mass manufacture. And you can see we sold 119 of these things to various backers and raised a little bit of money. And we were able to sort of figure out that programmable guitar boxes have a very limited market, especially if you charge too much for them, which apparently we did. Let's see what else we got here. So there's a bunch of stuff that you can check when your board doesn't work. Since the SPI is sharing a serial clock with the other devices, it's possible the serial clock got messed up. So that's something you can kind of look at on an O-scope. Sometimes SPI just acts weird. And this can happen because of a misconfiguration. Inputs can be left to float or allowed to go high when they shouldn't. You never get data out. Sometimes you have to look and see if things are being clocked correctly. Take a look at the SPI output and check it with a scope. Here's one thing that I was able to do inside of a little loop. I just did a printout of all of the basic MOSI MISO serial clock and serial select lines, and I was able to see exactly which pins had been assigned. That's kind of a sanity check, make sure things are wired right. That's a good thing to have done. And if you're ever wondering where your sketch is at, just go to the sketch and do the show sketch folder, and that'll bring you to the sketch location. So if you were to take a look at where this barometric pressure sensor is, you could go to sketch, show sketch folder, and then you'll see exactly where the INO file is. And you can go to other examples, and you can find that they have their own SPI library. And that's interesting, because if they have their own SPI library, that means they're shadowing the system library and they're doing their own thing, which could mean they're getting completely different results when they do their SPI than when you do it. And it's really good to know, what's in that code. So you might want to take a look at it, see if it's something you want to, have at, or at least look at. Be aware that this may not exactly match the system code that you've grown used to. Imagine, if you will, that you write a math program that works in radians, and somebody else overlays their math program that works in degrees. The compiler won't care. They both take in floating point numbers, but your answers will be radically different, and everything will break. So that adds a lot of variability to the experiment. So that's what I have for you for today. Hope you liked my little presentation on the SPI interface. Talk to you later. Bye.